Howdy, Math 330. I hope your MnM model, or penny model as the case may be, went well. Here is the data from mine. I started with 20 MnMs. In the next iteration, I ended up with 10. Then I ended up with 4, then 3, then 2, then that one lasted for a while before it ended up becoming 0. And notice that once I'm at 0 MnMs, that is going to continue for the rest of the experiment right there. So that's forever. I'm going to have zeros at that point. Now what we'd like to do is build a mathematical model of what we saw right here with our data. And it says let's attempt to build a mathematical model. Let's define the number of MnMs alive at the start of iteration n as a of n. What values would n take? What would a of 0 be in this take? And do we know what a of 1 would be? So right here, what is n in this table? And my question is, what is a of n in this table? And if you haven't taken a moment to think about this, please shut the video down for a minute and just take a minute and think about it. I'm of course going to go through and just give you some answers here. So if we want to model what's happening with the MnMs as a of n, then these values here have to be a of n. So right there, that 2, that should be a of 4, and right there that 4 should be my n right there. So this would be, so n would be equal to 4. Here we would be looking at n equals 0, and here we would be looking at n equals 1. So this would be a of 1. Now, do I know what a of 1 would be? Well, I do know that in my experiment it was 10, but in your experiment it might not have been 10, right? So I don't technically know what a of 1 is. I do know for sure what a of 0 is. By the way, a of 0 is of course that value right there. Now, if I want to, based on these observations of what happened and my assumptions, I would like to produce a reasonable formula that models what I see happening in this data right here. And I can come up pretty easily with a formula. Hey, a of n is going to begin with 20, so a of 0 is 20, and then each time I think I'm cutting that number in 1/2, so each time I'm modeling by 1/2. So I'm going to make that 20 times 1/2 to the n. Notice that a of 0 then is going to be equal to 20. A of 1 would be equal to 10, so that matches my data back here. Then I would have a of 2 is equal to 5. Now that does not match my data point right there. My a of 2 is actually equal to 4, and then you can figure out, hey, a of 3, that's going to be 2.5. Well, I can't get a value of 2.5 because I've always got an integer number of MnMs. A of 4 would be equal to 1.25. A of 5 would be equal to 0.625 right there. Check that with your calculator. Don't necessarily believe me on that one. Now, is this functional a reasonable model for what's going on with a of n? Well, I would never expect a function like this to exactly match my data, because this function I know is going to end up eventually with fractions, and my data is never going to end up with exactly with fractions. This model also, this is never going to get a 0 value in here, and I know I'm going to exactly get a 0 value. So is this a reasonable model for what's happening here? I think this is a very reasonable model for what's happening here. It very much models what should be happening in the process, but I'm modeling what I call a statistical process, or a process with some randomness in it. So I would never expect this to exactly match my data. How would I measure, and the last question that's here is, how would I measure my success as a modeler in my situation? Well, if I looked at a whole bunch of different runs of this data, I would expect that the trend for this function to look like the trend for the data and all of that. So that's how I would measure success. So I think this is a reasonable model. Now, there are some other models you could have come up with here. And in particular, you might have come up with a different model. You might have said, hey, a of n is going to be 1/2 of a of n minus 1. This is what we call a recursive formula for this process, and it says the number of MnMs in iteration n should be half what was in the previous iteration. Now, along with this formula, we also need to enter the initial condition a of 0 is equal to 20, because if we don't have somewhere to start that off, this formula becomes meaningless. So notice these two different formulations for the model. This a of n is 20 times 1/2 to the n. So if you give me an n, I can immediately calculate what a of n is. And this formula right here is kind of different. Here I've got a formula for a of n in terms of a of n minus 1. So if I want a of 10, I have to start with a of 0, then I have to calculate a of 1, then I have to calculate a of 2, then I have to calculate a of 3. I have to calculate all of those to get a of 10. So this formula to some extent is preferred because this formula immediately gives me an answer, whereas this formula, if I want a of 10, I'm going to have to do a whole bunch of iterations to get it. All right, so now we're on to the next experiment. So the next experiment is death with immigration. So this time, let's see if I can get this all lined up correctly with the document camera. This time we are going to permit immigration to recover the damage to our MnM population from death. Again, we're going to start with 20 MnMs. I am not starting with MnMs. I am using pennies today. Don't start the experiment until you've thought about what you will expect will happen. We're going to gently shake these M&Ms out onto a flat surface to determine for each M&M if it lives or dies. If the M shows up on top, the M&M dies. So if I get heads, that coin is going to die. Otherwise, there is life left. Upon death, we're going to remove those M&Ms or those pennies from our population. And then the very important change is that I am going to return 6 pennies to my population at each iteration to the survivors. Now, after I've put those 6 back in, now I'm going to write down how many I have that are still alive. So once again, we're asked to state our assumptions about this physical activity and to offer a description as to what we think is going to happen over time. I would, in particular, our assumptions are pretty much the same, are very similar to what we have before. The description is different. What do you think is going to happen? I would encourage you to think about what you think is going to happen with these M&Ms, or in my case, the pennies for this model. Now we're going to actually perform the experiment. I'm just going to show you what this looks like. So I'm going to shake this up. I'm going to shake my pennies out. So the ones that were heads up were going to die. So I'm going to just take those out of my population really quickly. Those live, die, 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 you penny, die. All right, so this time I ended up with 1, 2, 3, 4, 5, 6, 7 surviving pennies, but now I've got to do the immigration, so I'm going to take 1, 2, 3, 4, 5, 6 back in. So let's see, I had 7 plus 6, so what am I going to record in my table right here? I am going to record a 13 right there. And now I'm going to take those extra pennies, I'm just going to push them away. I'm going to put these back into my cup, and I am just going to do this again. So I would ask you to please take some data. Please go at least to about iteration 10. If you aren't willing to go all the way to 12, please get a fair amount of data so that you can really see what's going on. Check to see how that matched up with your description of what you thought would happen, and then see if you can build a model for what's happening right here on the back. Thank you very much for listening. Please go do that, and I will be back with a new video in just a minute.